Okay. Let's look at another message type next. Called TCNBPDU. Then before you talk, I will draw a topological map. Let's see if it's necessary. Let's talk about the environment first. As long as you understand the environment, this message is easy to understand. I now draw 3 devices first. Still connecting the cable. Then after our choice. Finally, this port was elected as a blocking port. That is, this port does not perform traffic forwarding on a daily basis. Let's give them a name first. There are 3 devices in total. The one on the left is still device A. On the right is still device B. This is device C. Only these devices will not work. I still have to draw 2 PCs. Suppose a PC is connected under one end. Draw another PC here. We now assign 2 interfaces to device C. For example, this interface is C1. This interface is C2. The same is true for device A. This interface is A1. This interface is A2. Device B is not needed here. Assuming the device on the left is not a PC. It is a server. On the right this is a normal user's PC. That is, there is such a server in the intranet. After we network based on the switch. I hope this PC can access this server every day. For example, here are some OA systems of the company. So, now I want to access it daily. Then the way must be passable. Once we have communicated the data, send this data here. Finally, send data packets and reply data packets. Then everyone should know. There will be a MAC address table on both devices. Suppose now a MAC address table of device C. As such a device, it must have its own interface. Suppose the interface is C1. C1 corresponds to an address that is the address of the PC. I actually told everyone. When the data is being encapsulated as a whole. In fact, the interface of the switch does not have a MAC. So now send the data here. From the C1 this learn the MAC from the PC. Then the final data if the past. Reply packet. Remember ARP? Send a broadcast message. Then all devices that receive have a reply. For example, PC wants to request server. The IP address of the PC is 1.1. It is 1.2. It needs reply packets. If the message replied by server passes through the C2 interface, then C2 will learn server's MAC. That is, the address corresponding to the C2 interface is the MAC of server. Here is the MAC address table for device C. Same. Let's take a look at the MAC address table of device A. For device A. Now under the A1 interface. This must be a PC. This is the server under the A2 interface. When it receives data now. Messages received from PCs here. A1 corresponds to PC. If the future server replies to the packet, return to device A from A2 interface. This A2 interface is learned here is server. So now you will find. Every day when we communicate. This is how the PC accesses the server. Because now the data has arrived. We need to look up the table. Check the table here. This is requested through ARP. The sent message can be learned by the devices along the way. The MAC address table was built successfully. Then it goes to the server and sends it from interface 2. Then send it. Device B will not be discussed. Because it has nothing to do with it. Let's discuss a scenario. When one day the line between device A and device B is broken. Then the blocked port on device C will become a designated port. The direct link is down now. For device C. It is indirect. It is this picture. But we are not discussing this picture. We don't discuss forwarding time. It stands to reason. This interface should start data forwarding. Assuming that the 50 seconds have now passed. It has become the state of forwarding. So do you think there is any problem with this forwarding process? Now the line is broken. Let's see how it is forwarded. As a switch. The PC still accesses the server. Data arrives at the switch. The switch needs to check its own MAC address table. Then the server is on its number 2 interface. It corresponds to send out from here. The data still arrives at device A. Device A table lookup. Send from its port 2. After sending out. Found a problem with this line. There is no way for this message to reach the server. Some friends may find it strange. Now this interface forwards. Shouldn't the data go like this? How could it go up there? We have a question. The data arrives at the switch here. The PC is only responsible for sending the data. The switch forwards based on the appearance lookup table. In the MAC address table. It is going to server now. Server corresponds to C2. It will only be sent from C2. If this interface is C3. It hopes to send from here. Because it forwarded. But the switch knows the link is down now. That is. The MAC address table in the switch does not care about these. For the MAC address table. Both interfaces C1 and C2 are working normally. This interface is not down. Then this appearance exists. And the aging time of the MAC address table is 300 seconds. For switches. 300 seconds is 5 minutes. The MAC address table has always existed. Under what circumstances can it find that we should switch links? There is a situation. Wait 5 minutes. After the appearance of the server. Through the C2 interface naturally ages. Let's ping again. It will resend the broadcast to request. And the embarrassing place is. The other party is a server. It will not actively send data packets. It's okay if the other party is a PC. Because if the PC communicates. If this link is broken. It must send ARP. After making an ARP request. Data will come from here. If the data of server comes from here. Suppose this interface is C3. You will map such a MAC to C3. Because one MAC address cannot correspond to 2 interfaces. It originally corresponds to C2. But it received from C3. It will refresh the address table. But unfortunately, its peer is a server. The server will not actively send data packets. It can only wait for passive access. That is, such a representation will not be refreshed. A PC can only wait for it to age naturally. When it gets old, the PC needs to request the MAC address of the server again. The ARP aging time on the PC side is relatively long. 20 minutes. But its data goes to the switch. This is an unknown unicast data frame to the switch. The switch needs to perform flooding. Then this data will be sent from this interface. Will be sent from this interface. But this interface does not work here. So the switch cannot learn server from C2. Send it here. The server will reply a data packet to it from the C3 interface. So now device C can update its appearance. It turns out that this server corresponds to the C3 interface. Once the MAC address table is updated now. This PC then visits the server. The switch knows that it should be forwarded from this interface. Will be sent. So wait at least 5 minutes for this time. For the current business flow. STP is to quickly complete the switch. Stop talking 50 seconds now. It's 30 seconds. The environment can't afford to wait now. If it really takes 5 minutes to switch. No one will use this agreement. If the link fails now. Our current projects will combine traffic monitoring. 5 minutes is enough time for me to call the police. Then I rush to the computer room to see the configuration. Too long. So this is definitely not optimized. So the reason why this happens. Because our collective information. No way to get timely updates. This link is now in forwarding state. But the device itself doesn't seem to know. That's why messages like TCN-BPDU appear. Okay. Our next picture. I will draw more pictures today. I draw a better understanding. For example. Now here are some devices. For these devices. For example. Now this device is originally connected to other. But at some point one of its ports becomes forwarding state. Then it has to tell other devices. It is now switching state. If the interface is now in the forwarding state, then please pay attention. Will be controlled by the root port on this device. Send a BPDU message upstream. Called TCN-BPDU. It is a topology change BPDU message. Will be sent by the RP port of the device. Send this message to the upstream device. Tell it. The interface of a device below is now forwarding. So it will send this message to the upstream. I will simply draw its process. When the above device is received, it will be from its own designated port. Send a BPDU message to the downstream device. Because the daily designated port sends BPDU out. Usually this is the designated port. Below are the root ports. It sends configuration BPDU. But what is different in the configuration BPDU? It's in flags. There is a man named TCA. It will set this bit to 1. Originally this bit was 0. But it sends a set bit to 1. This message means topology change confirmation. Means it's off now. It is replying this confirmation to the downstream device. Then it will continue to send TCN-BPDU up. Tell the device above. Now the device below has changed. I draw shorter. This goes straight to the root. If it is not root, the upstream device will then send a configuration BPDU to the device. Tell it to stop. Then it goes up. Keep sending it until it reaches the root bridge. After the root bridge receives, it sends a configuration BPDU. Among them, except TCA is set to 1 in flags. It will also set another TC to 1. TCA is set to 1 to tell the device not to send. Secondly, it sets TC to 1 at the same time. The representative tells the entire network to refresh the MAC address table now. It is equivalent to replying to a message. Sent a message. But did 2 things. TCA is to tell the lower equipment not to send. Secondly, the TC will always forward the message downwards. Because this is a configuration BPDU. Other devices are to forward the configuration BPDU of the root bridge. The meaning of this TC setting is: tell all devices it's time to update their MAC address tables. Then all devices will clear their MAC address table. Relearn. It is equivalent to the fact that there is a server corresponding to C2 in the device. As a result, it is sent from C2 every time it goes to server. For now, these MAC address tables are emptied directly. Then any data sent by the PC now. It is an unknown unicast to the switch. All switches must perform flooding. As long as the switch performs flooding, then it will learn the correct server MAC. Then put it in your address table. So the process is very fast. That is, we manually cleared the old one that should have been. As long as there is such an interface in the environment. From the original blocking to forwarding. It means that the topology of the entire network must have changed. There must be an interface state change. That means The things stored in the MAC address table in some devices are wrong. So be conservative. Everyone started to refresh the MAC address table. Then relearn. That's what I mean. This message has a sending time. It will send a total of 35 seconds. The first time you start sending down. Send once in 2 seconds. Send in 35 seconds. Then stop. Keep sending. Until it is confirmed that all devices on the entire network receive this message. Configuration BPDU and TCN BPDU are two packet types. How to distinguish? Distinguish in BPDU type. One is configuration. One is TCN. TCN is dedicated to the interface below to become forwarding. Reported upwards. Then the reply is always the configuration BPDU. It's just that it will modify the parameters of the two flags inside. Then send down. TCA means it knows and don't send it. TCA represents the entire network to refresh the MAC address table. Okay. Then we basically talk about STP is almost the same. Now for STP. It also doesn't have much configuration to speak of. It is more about some understanding of the entire agreement. Very theoretical in the NA stage. When you reach the NP stage in the future, you will learn a lot about some protection mechanisms of BPDU. Include some switching mechanisms. There will be many experiments. Let's talk about DHCP and CDP next. DHCP is called Dynamic Host Configuration Protocol. That is, you can configure some address parameters for it without static manual configuration. When we run the DHCP protocol in the network in the future, I can make some terminal devices automatically obtain some online parameters. For example, I want an IP address. We need to manually configure. I want a gateway. We also need to manually configure. I want to write a mask. Also requires manual configuration. In the future, use this device to access some domain names on the public network. I have to request its IP. So how do I know its IP? DNS is also configured. These parameters are when we go online normally. Some parameters to assign. Then let's take a look. For me now. Look at my network card. There will be a DHCP enabled. Indicates that the device is now enabled with DHCP. There are a few things in here. One is called an IPv4 address. A subnet mask. A default gateway. A DNS server. These are the four more important parameters. It is the core content of our explanation today. When we talked about the reference model earlier, there is a protocol stack. Now if this device wants to complete the communication normally. In fact, we open the protocol stack of TCP IPv4. This is the system comes with. But you will find, when I am getting parameters online now, what is actually used is to automatically obtain. In fact, it is DHCP. Then we can also change it to use the following IP value. Manual configuration. So if we want to specify the device to configure the following parameters: IP address, mask, gateway, and DNS server. So these parameters are actually. Now a computer must need some parameters when it wants to complete the communication normally. Let's recap. What is the role of these parameters respectively? First of all, the IP address is the identifier of a device. Network communication uniquely identifies the logical address of a device. What does mask mean? An IP address plus a subnet mask. You can confirm which network segment the device belongs to now. Direct communication on the same network segment. Communication between different network segments requires a gateway. For example, this is a router. This is an interface. This is a gateway. This is a PC. Then PC will communicate across network segments in the future. It's going to request the gateway's MAC. Then the gateway must be on the same network segment as it. That is, it belongs to an address of the internal network port. These are the knowledge we talked about before. Our daily internet access must cross network segments. So these parameters have. We will not learn too much about this DNS. For example, internally some devices to access Google. This has a router as an egress. Then make some connections below. This router is connected to the operator. Suppose the operator is connected to a Google server. Suppose the address of Google server is 123.1.1.1. But when we actually go to Google, in fact, it is not directly sent a data. Source IP is 192.168.1.10. The destination IP is 123.1.1.1. Not a direct encapsulation. Find it directly. But across the public network, there will be other devices designed to help us do other things. This device is called a DNS server. This server will store a lot of correspondence between domain names and IP addresses. For example, www.google.com. Its corresponding address is 123.1.1.1. Normally, when you visit Google, more domains that visit Google. For example, ping www.google.com. Ping is a domain name. But logically, communication should be based on an address. Can't communicate with a domain name. Actually, before you go to actually access the Google server now, we'll first send a message. The destination of this message will be the DNS server you configured. The message content is the IP address corresponding to www.google.com. You would send a packet asking. It receives the message and retrieves it locally. After that, it will reply you with a message corresponding to this message. It will give you the corresponding response. So now the host gets www.google.com corresponds to 123.1.1.1. Then you go to data encapsulation. Only then will the destination IP be written as 123.1.1.1, which is equivalent to. You will send this message to 123.1.1.1. Instead of sending directly to 123. 1.1.1. But for us, this thing has no perception and we're done. But you need to know. We will have a server like this. Actually, we all need to configure the host. But we don't seem to have configured the internet now. Because what we are actually using now is the way of automatic acquisition. DHCP is a must. It's not just a matter of cumbersomeness. Manual configuration has some disadvantages. For example, I am now going to configure an address for my computer. I choose manual configuration. First of all, manual configuration is a lot of work. You can easily configure address conflicts. For example, you are now operating a network. There may be hundreds of devices in this network. You need to plan the network segment. You also have to remember who used each previously assigned address. You can't assign duplicates anymore. Otherwise, address conflict. It's easy to go wrong. It can be avoided. But there is one circumstance that cannot be avoided. Or you can't use manual configuration. That is, when you are in a public place. There is no way to configure it manually. If you go to a coffee shop and have a cup of coffee, you can't tell the clerk. Connect to their Wi-Fi. Let them assign you an IP. This is impossible. If you want to connect to the network inside the coffee shop, surf the web through their devices, you need to configure an IP. Then this IP needs to be on the same network segment as the internal configuration of the coffee shop. Just find the gateway. At least there must be parameters in the Internet address configuration. If we all use manual configuration now, then the Internet will be very inconvenient. So there are some scenarios where there is no way to manually configure, because this function has a relatively certain threshold, and it's too much trouble. So we now use more dynamic configuration. Dynamic configuration is what we call DHCP today. Dynamic configuration requires running DHCP between the server and the client. It's easy for the client. You don't need to type the command. The client is a graphical interface. You just need to click this directly to run the protocol. But the router side needs to be configured. Then let them be based on the DHCP protocol. Automatically send some address parameters to the host. This DHCP server does not need to purchase the hardware of the DHCP server separately. For example, it can use a router, layer 3 switch, firewall. This can be simulated. They can simulate a DHCP server like this. That is, DHCP server configuration can be done directly on other devices. You don't need to buy a separate server. Let's take a look at how DHCP works. Look at this picture. There are two devices. The device requests an address from a server. Then assign the address. Okay. Let's look at the message type next. This is a topology. Let's wait for the configuration. It will be configured as a DHCP server. Next, here are the two devices. This is the client. It is a very standard CS architecture. It's a client-server architecture. The client asks the server for some services. The server provides corresponding services to the client. This is called the CS architecture. In this schema type, we need to know how DHCP works. Then we need to know which messages DHCP will send. Let's just look at the first four. We don't really need the latter two during the request phase. For messages, let's take a closer look at the sending rules. First of all, here is a DHCP discover. This is called the seek message. When the client looks for the server, first it sends the message. Since it wants to find this server, definitely send packets. If you send a data packet, you must perform data encapsulation. If you want to package. So how to encapsulate the source IP and destination IP? This is the only interesting thing in the boring configuration in DHCP. Now there is no IP to request IP. That must have no source IP. But if you don't fill in the source IP, can't send packets again. When we talked about IP addresses earlier, speaking of some special IP addresses, for example 40, in addition to representing any address on the entire network, make a default root other than. It can actually represent the unknown. Represents no IP now. The destination IP is called the network-wide broadcast address. Is also a restricted broadcast address. 4255. Binary is all 1. For 255 reps. Now all devices only need to receive this message. Must be processed. This is called the network-wide broadcast address. So the first message sent by PC1. That is, this DHCP discover is such a message. The second layer is packaged like this. Then once the message is sent, the switch only needs to be powered on. Then both PC4 and R1 will receive. After receiving R1, found that a device is asking it for an address. It is a server. Then it has to reply to the address. It provides this service. When R1 replies to it, It is necessary to reply to it with a second message type, called DHCP offer. There will be some parameters in the reply message. It will carry what address it wants to assign to this device. And I want to emphasize to you a question. When the PC sends a message, the second layer of encapsulation source MAC must be itself. The purpose MAC must be all one. Actually, when the server receives this message, it is able to learn this PC's MACs. So, when the server replies to the packet, in fact, it can be unicast back and forth. Because as a PC, it will look at the second floor first, then look at the third floor. It can directly turn the destination IP into a unicast inside Cisco when it responds to an offer broadcast, although it can learn the MAC address of PC3. But it doesn't. It will send a broadcast. Then both devices can receive. Certainly. Because for the device is the request made by PC3. So PC3 will receive. PC4 is not requesting now. So it's not replying to what you sent. Just know the way. This is called a DHCP offer. It will be carried in the offer. What address do you want this device to use? For example, you have planned some addresses here. Used it. Then when it received, it will reply again. It will reply a request. In this request message, will carry some address it now wants to use, including the server it chooses. Some students may ask, what is the selected server? Isn't this just a server? Sometimes we are in some network environments. There may be multiple servers. It's a backup problem. For example, now there are a lot of devices in the network. I just point to a server to assign me an address. One day it suddenly went down. Now what about the addresses below? So often there may be multiple servers in an environment. If there are multiple servers, it will face a problem. When the PC sends a broadcast packet to find the address, both servers will receive. Then as long as server receives it, it will reply. Now the address that the PC replies to is not the same. This PC is about to choose whether to use device 1 or device 2 as your own server. And what exactly is the address given to you by device 1? Or the address given to you by device 2? So in this DHCP request, we'll carry the address you want to use, and the server you want to choose. And the packet you sent is a broadcast packet. Suppose now you want to select device 1. It assigns you an address of 1.1. Device 2 assigns you an address of 3.1. It is also possible that it is not on the same network segment. For now, you send a broadcast packet. It will carry that you want R1 to be your server, and you want to use the address 1.1. You send it as a broadcast on behalf of. Both devices can receive. Then device 1 knows to use its address. It will give you an ACK. Make a response to this message. And is locally documented. Why send it to this device? Because it is broadcast. So R2 can also receive. R2 received and found that the choice is R1. It takes back the allocated address. For other clients in the future, this broadcast message not only told the server you want to choose. Let the server you don't want to choose know that you are not selected. So this is a very optimized mechanism. Sending a broadcast is equivalent to telling everyone. To us. Here is a bogus DHCP attack. When you reach the NP stage in the future, you will learn DHCP snooping. Then you will solve it. For example, some devices are privately connected to the network. Privately entered a DHCP server. Or privately came in a TP-Link. Because TP-Link opens some DHCP functions by default. If the TP link is privately connected in the internet, it may cause your device to be unable to connect to the internet now. When you send a message, maybe it replied to you first. We didn't say who it would choose. This is very simple. It receives the message from who sent it first. Whoever it chooses. Device 1 first sends it. It selects device 1. Device 2 first sends it. It selects device 2. Finally, the client sends a confirmation to it. Then this address is used for it. The local will remember which MAC this address is used for. After that, it will not redistribute this address to other devices. Here are some conceptual parts. Let's look at the configuration next. The configuration is also very simple. Throughout the NA phase, many things are actually a basic understanding. So it's not hard to configure something. We first turn on these devices. Some students may ask, under what circumstances will the client reject the offer? The client has a release address. You can release it manually, but it won't refuse, because this service is initiated by it. Suppose it now initiates a message. Want an address. The device gives it an address. Then it refuses. This situation does not exist. Only two cases. One is that it is going offline. The second is that it wants to configure manually. Then it will actively send messages to the device. Release the address allocated by the device. It will not take the initiative to reject the offer. If it now receives two messages at the same time, then it will choose the first, not the second. Because there is no need. Unless there is an artificial configuration. It doesn't want to use DHCP anymore. It will release this address. Okay. Let's configure these PCs. The switch does not need to be configured. Open this router first. What we use today is a global allocation of DHCP. The allocation we are talking about today is also a commonly used one in DHCP. How should it be defined? I want to treat this device as a server. The device below is the client. The client asks the server to get the address. First of all, we need to define an address pool here in server. In this lesson, the PC does not need to configure IP, mask and gateway. Let's look directly at R1. VPCS is virtual PC. First come in R1. We first configure the address for the interface. E00 interface. Suppose the IP address is 192.168.10.254. This is an interface address. Next configure the mask. 3255 and 10. No shutdown. Now that I want to use R1 as a DHCP server, then I must define the address pool. IP DHCP pool. You can see. Followed by name. We can name it. Call it P1. I now define the name of an address pool. Certainly. In the future, if you assign based on different departments, when you reach the NP stage, you will learn DHCP relay. Then when we go to define the name, you can write pool RAND, pool technology, pool finance, etc. It's all okay. Write a P1 now. Just know it. I now want to define the assigned network segment. That is, now these devices have to find R1 to get the address. Which network segment is the address that R1 wants to assign to the device? It has to define. For example, I now define a network segment. Type network. Then enter a question mark. Now you can go and specify a network segment. For example, 192.168.10.0 network segment. 24-bit mask. It's okay to write like this, because the network itself is connected to 10 network segments. I will write it as 10 network segments for you. After assigning the address to the device. After the device gets the address, it can directly connect to the interface of R1. R1 is in the 10.0 network segment. The device asks it for an address. R1 assigns the address of the 10.0 network segment to the device. Then the device can directly find R1 in the future. So usually we deploy this device of this DHCP server. It can also act as a gateway. This is the deployment logic for the device. For us now, when the future PC is looking for it to get the address. In Cisco, it is assigned from small to large. That is, PC1 will get 10.1. PC2 will get 10.2. Then after I configure the network segment, I want to set the default gateway. The default gateway is usually set to itself. 192.168.10.254. Then we go to specify the DNS server. Suppose we configure 4.8. After configuration, let's take a look at our configuration just now. Do show run. IP DHCP pool. Let's look at the configuration of the DHCP pool now. We first define a network segment is 10.0. After specifying the gateway is 10.254. Then configure the DHCP server to be 4.8. OK. We are now done configuring. After the configuration is complete, the host can be dynamically obtained. This operation is very simple. IP DHCP. This is PC3. You see there is a DORA in front of it. This string of characters represents these. It happens to be the first letter of the message. The first, D, stands for DHCP. The second, D, stands for discover. O, stands for offer. R stands for request. A stands for ACK. Here are the first 4 messages. Represents that it has now gone through several processes. Then got a 10.1 address. Gateway is 10.254. We can view some detailed parameters. Show IP. You can see. Here DNS is 4.8. The network segment is 10.1. The mask is 24 bits. Gateway is 10.254. This is 4.8. DHCP server is also 10.254. This is a normal way to get the address. Let's talk about another way now. You will find, in a business, a lot of things are online now. For example, the picture here is a PC. But it could be some other device. It can be a printer. First of all, you need to know. Now this PC may go offline and shut down someday. For example, I got off work today. Just offline. This address will be released after going offline. I don't need this anymore. Need to be offline. This address is recycled. Then the server will take this address away for other devices to use. I came to work again the next day. The PC wants the address again. The PC will look for it to get the address again. So this time it got the address. It may not be exactly the same as the previous address. Doesn't really matter for PC. Because we are online. It doesn't matter what address. As long as it works. But like some equipment fixed inside the company. Devices like printers and cameras. Many cameras are now connected to the internet. Like I'm in a surveillance office. I can remotely view the information of this camera. Because it is also on the switch. Can be attached. So it's online. Then if you are online, we are going to do some information exchange. With the address of the switch here. And for many monitoring software, we can directly fill in the address. Then to complete the information exchange communication. I don't want this camera address to change every day. Sometimes the camera is turned off at night. Get a new address the next day. I rebind its address on the monitor. This is too much trouble. Second, as a printer. Now some printing in the company is connected to it through IP. We connect to this printer in the software. After connecting up, we want its IP address to remain unchanged. The printer generally does not power off. Otherwise, every time I use this printer, I have to check its IP again. Then rebind. To be able to connect to the printer remotely. Let it print for me. This is really too much trouble. We will directly bind one today. If you are interested in the excluded one, you can take a look at the command. Actually it means. Let me first explain to you what exclusion means. In fact, many orders. I pick some typical ones. Exclusion is. I now have a large network segment. Then in the network segment I can specify. A certain part to a certain part of the address is excluded. Then in the future, it will be assigned to the printer. It will not be assigned to printers within this range of addresses. But what we want today is assign a fixed IP to the printer. Keep its address unchanged. We call it to issue a fixed IP for a fixed MAC address. Trouble in Cisco. Let's take a look at how Cisco configures. These are some of the more commonly used commands. Or configure it on the server. Before configuration, we need to check the address of PC4 first. Show IP. Let's see its MAC. I will copy it. After copying is complete, we exit now. Now go to configuration mode. To define an address pool. That is, on 4 devices. If you want to issue an IP for a single device, you need to define a separate address pool for this MAC address. Give it a separate IP. IP DHCP pool VPC4. Now after defining the address pool, I want to assign a separate address. We can enter a question mark. What we just wrote is network. Defines a network segment. But now I just want to configure it for a single host. So we don't need to define the network segment here. Enter host directly. I want to assign an address to this host A. Let's say I assign it 192.168.10.123. 24-bit mask. Because we are an address assigned. So just type host. Do not enter network. Then configure the gateway for it. Default router 192.168.10.254. Then DNS. For DNS. In fact, we can write multiple. For example, 1.1.1.1, 2.2.2.2. It's all okay. Enter preferred and alternative. The last step I want to bind it to MAC. The command to bind MAC is client identifier. In fact, it means its MAC address. We'll just paste it right now. This is the MAC address of PC4 we just looked at. You can't just press enter. I put a question mark here for everyone to see. When you configure here, must conform to this format. Now you will find it does not conform to this format. Not only does not meet. Add a 01 before the very beginning. Cisco has to be configured like this. 01 stands for Ethernet. So after that, separated by 4 digits. The last 04 can be written here. Then press enter. Bind now. I have now defined an address pool. Then I put a 10.123 address like this. Assigned to such a MAC address. Let's take a look at PC4. I now let it dynamically get an address. IP DHCP. Okay. I get it now. 192.168.10.254. That's what we're talking about. Issue a fixed IP for a fixed MAC. This is a small application in DHCP. We don't experiment much today. It's not hard to do. The configuration may be simpler than when talking about VLANs before. I turn it off first. Before talking about the next knowledge point, I first open the environment. Otherwise it's a waste of time. After opening it, run it first. Everyone should have a simple understanding of DHCP in the NA phase. In the future, we will learn snooping and relay in the NP stage. It will be relatively more difficult. I saw some friends ask, how many IPs in the company need to build a separate DHCP server, instead of using the router to open the DHCP service? It's not just about the number of IPs. It also has something to do with your network planning. But usually, medium and large enterprises may have dozens of devices. Generally speaking, DHCP can be done by simulation. But it mainly depends on which node your device is on the network. If the core equipment in the network has to undertake some other functions, then usually we don't deploy a DHCP server to it. That is to say, it still depends on the location of the device where you deploy this protocol. Usually it is not directly related to IP. Mainly depends on your business type. Generally speaking, the device can almost connect to the DHCP server, because it bears a relatively large traffic flow. And possibly more. Make a backup. Okay. Next we talk about the Cisco Discovery Protocol. This is called CDP. Discovery of interconnections between devices. The content of PPT is also very simple. As long as the Cisco devices are now connected, then the protocol will be run accordingly. I can check what devices are connected to the device now. In fact, it is to help you draw topology. It will tell you what kind of equipment is there next to the number 1, number 2, and number 3 ports of this device. It is equivalent to providing you with some information. But it's only available inside Cisco. CDP does not require you to run this protocol. But you need to configure the address for this interface, because they interact with some data. This is our device. I have already configured the address on the device, because this does not need to be assigned in class. This is just for show. Show IP interface brief. Let's check. I am under interface 2 of R1. Configured a 12.1.1.1. Then configure it under the R2 interface. Show IP interface brief. I have allocated addresses under the R2 interface. Same for R3. I only configured the address. Protocol also does not work. Then R4. Okay. We are all configured. Let's take R2. Because it connects more devices. Very simple one command. Show CDP neighbors. And then press enter. This thing doesn't need to run. The device only needs to be turned on. This command will come out. But if there are no neighbors, now these lists are empty. But you can see the name of the watch. It will now write you. Let's decipher what it means. I'll check out the neighbors of CDP now. First we look at these parameters. I will pick a few more important ones. Now here, R stands for router. For us now. View current neighbors. Has a neighbor's name. Because they have some messages with each other. It means. Let's take R3 as an example. R3 to R2. The local interface of R2 is. From which local interface is R3 discovered? R2 discovered from the local 02 interface. So this hold time is how long the two of them have been connected now. We don't have to worry about this. Further down here there is a platform. Shows Linux and Unix in the emulator. But in the real machine, this place shows the device model. But it has to be a Cisco device. In my emulator it shows such a Linux-based platform built. Because it is virtualized. So it doesn't have a device model. This also has a port ID. The port ID is the interface of the other party. That is now the local 02 interface of R2. The connected R3 interface is the 01 interface. From this diagram we can draw. Let me draw. We can blindly draw the topology. After you reach the NP stage, you can learn OSPF like this. Let's do a simple demo today. For example, this device is R2. There are now 3 wires connected to R2. They are its 2 interfaces. 1 interface. 0 interface. The 0 interface is connected to the 3 interface of R4. The 1 interface is connected to the 2 interface of R1. The 2 interface is connected to the 1 interface of R3. It is equivalent to this thing is to help you draw topology. Cisco equipment is available. All the drawings in this courseware can be used. But the premise must be Cisco equipment. Let's take a look at this graph. Is the same as what we just wrote. It's just that my painting is not as comprehensive as it is. Let's take a quick look. Interface 1 of R2 is connected to interface 2 of R1. R4 is connected to the 0 interface of R2. Opposite is the 1 interface of R3. Connected to the 2 interface of R2. It means, when you view neighbors on your device, you can quickly find out what equipment is connected to this device. And connected to which interface. Just to help you sort out the topology. Because when you come to the computer room in the future, you will find the wiring in the computer room may be messy. For example, you go to a project cutover site. Probably because the person who worked on the project before was not present. A problem needs to be cut over. If there is no topology, you can check it. Simply look at how the specific topology is connected. CDP is this function. This does not need to be tested. If you want to experiment, configure an interface address. Then you can see. Okay. Let's talk about ACLs at the end. Relatively speaking, ACLs are quite common. For ACLs and NATs, you may not know very well, but you may have heard of both techniques. The configuration is also very simple. ACL is called Access Control List. As the name suggests, it is for access control. It is actually equivalent to a function. Or you can also understand it as a strategy. Based on it to define the communication of the future data as a whole. Access Control List. When configuring in Cisco, we call it Access List. Techniques we have learned before. Either routing or switching. In fact, we all hope that the network can communicate. So we now pass the ACL. In fact, it is hoped that the network will not work. Of course, this impediment is conditional. We can control it by a means. That is, control whether some data in the network can communicate normally. This is the concept of ACL. Or, it is equivalent to restricting internet traffic in a certain range. You can do some other strategies based on it. It's not just a question of whether it works or not. We can also grab some data based on ACL. Perform some encryption on the data. Etc. Is equivalent to. You want to grab some data. Then operate on the data accordingly. There are quite a lot of controllable directions for this operation. ACL first has the concept of a list. You can understand this list as a list of arrests. If it meets the conditions of the list, it will be captured. ACL is divided into two steps. The first step is that we need to match the data according to some matching conditions. Then we will define actions for it based on these matching data. Action is nothing more than two. One is called permit. The other is called deny. That is, for a data matching is either permit or deny. Let's take a look at the PPT. It has two application scenarios. Let's read it together. This drawing is actually quite intuitive. First of all, for internal. The two network segments are 1.0 network segment and 2.0 network segment. What about the two network segments? This red line is the 1.0 network segment. You will find the 1.0 network segment can access the internet. But the 1.0 network segment cannot access the company's internal server. The 2.0 network segment can access the internal server. But the 2.0 network segment cannot access the internet. It's like your company's finance department. This is the R&D department of your company. The R&D department accesses the internal server storing R&D data. Then other departments of the company do not have the right to access. The daily security requirements of the R&D department are relatively high. Some devices cannot be directly connected to the internet. Therefore, the planned 2.0 network segment does not allow internet access. For data sent in the future, we can here on the router do some corresponding ACL formulation. If the future matches the 1.0 network segment, then you can go online, but can't access it. If the future matches the 2.0 network segment, you can't surf the internet, but can access it. Let's do some targeted traffic filtering. This is called an ACL. Okay. Let's move on. This is another application scenario. Stream of interest. In the future, everyone who learns NP may come into contact with this thing. Let me introduce. Now the data can be matched according to the source IP address. For example, now the data is sent from this device interface. Then I can match the data. Take corresponding action. Assume that the red 1.0 data sent over is now matched. Then send it directly. It's like not matching. In fact, it was sent directly. Sent to the internet. The blue one is the 2.0 network segment. Stream of interest. This is a name for flow. After matching, you will find it encrypts this data. You will learn VPN in NP in the future. Then you will know why now when forwarding via the public network to encrypt some data. Because some internal company data may be passed on in the future. But I don't want to set up a dedicated line for cheap. However, the transmission of data must have some privacy guarantees. So we want to encrypt the data. For example, this is a head office. This is a branch. Some data is transmitted between the two through the internet. But this data must have some encryption protection. For these data, encrypt on match, and then sent to the peer. So this is a different application scenario. That's normal. The traffic coming from this network segment will go online normally. Also take the internet. But without encrypting its data. Because it's not confidential data. This is the application scenario of the ACL we mentioned. Let's talk about the classification of ACL next. In fact, you can understand ACL as a tool. It is a very flexible tool. Match various data in the network. ACL according to different matching conditions can be divided into two categories. One is called the basic ACL. One is called advanced ACL. The basic ACL can only be matched against the source IP of the data. That is, it can only get the source IP. It's imprecise. In fact, it has a wider range. So we sometimes feel it is a bit inappropriate to use basic ACL, because the entire range it matches is actually larger, not refined. For advanced ACLs, it can match these. This thing is called a quintuple. The 5-tuple refers to source IP and destination IP in layer 3, plus the protocol in the 3 layers, plus the source port and destination port in the 4th layer. We call it a quintuple. That is, in a stream of data, there are some parameters that are the same. We don't have a particularly detailed understanding of TCP in our Cisco courses. Advanced ACLs can be matched based on 5 tuples. That is to say, I can now pass the form of source IP and destination IP plus protocol, even the form where all the parameters are connected together, to match the previous data. It is more precise. So here are some differences between them. So how do you know whether an ACL is a basic ACL or an advanced ACL? When we define ACL, there will be a number on the back. If the number is between 1 and 99, then you can only configure the source IP. If it is between 100 and 199, there are more parameters that can be configured later. Define the basic ACL and advanced ACL based on the number written behind the ACL. Then define the range of parameters that can be matched inside. In fact, we don't have many matching parameters for ACL, besides being a list. In fact, there is another thing called rules. So we just want to define. For example, ACL, we write a number. It's like a list. You can think of it as a catch list. In this list there will be different rules. It's like the cops can make a catch plan. That's in the plan. Many people can be arrested. Many cases may be parallel. Assume that prisoner A is caught, sentenced to 3 years in combination with its case. Prisoner B sentenced to 4 years. Prisoner C sentenced to 6 years. Other inmates detained. Each arrest plan does not only arrest one person. Same. The ACL list is equivalent to a plan. It is not only for one data or a string of data to perform actions. It can also match multiple data at the same time, and then perform different actions. This can all be achieved in a list. We call this a rule. That is, different rules catch different data, have different actions on it. Multiple rules can be defined in an ACL list. Containment, according to different rules, can take different actions. So ACL is like a filter. Different filters can be used for different data. It's just a function in the device. We can't talk about configuration today. Let's start with some basic questions. There is only one relatively difficult knowledge point in ACL. It is to perform the hook under the interface. Many friends will forget this configuration until the end. For example, this is a router. For routers, surely there are lines on both sides. Assuming it's not currently enforcing any ACLs. Do not do any ACL-related functions. It is normal data forwarding. A data will be from here into this device. If there are no restrictions, by default, layer 3 will forward according to the routing table. 1 to 99 is enough, because later data comes in. May also search to make the corresponding match. Generally speaking, there may be only a dozen or 20. Too many words are actually unnecessary. Okay. Layer 3 is actually a routing table. That is to say, if now the data comes in, it does not impose any restrictions on the ACL. It directly looks up the table and forwards, since it wants to control certain data. At least do it. Either don't let this data in. Either don't let this data go out. If there is no restriction, The data will come in. When the data comes in, check its routing table. Check the table and go out. Then it can't hold the data. So all it can do is, or don't let it in, or don't let it out. Gotta have a control over it in one place. So how to control the data on the router? Data coming in and going out is actually for the interface. Router interfaces are directional. I've been emphasizing this over and over again. The interface of the device is directional. It has both receive and transmit directions. For ACL, it is a function. If an interface receives data, then this interface is an entry point for data. If an interface wants to send data, then this interface is an exit for data transmission. Therefore, the interface has an inbound and outbound direction at the same time. But for data, if data is sent from left to right, in fact, the interface on the left is the entrance for it. The interface on the right is an exit for it. The access list hangs under this interface. Please pay attention to my wording. It is hanging on. That is, since you want to control the data through it, then you have to make this control method on the interface. You need to check according to the data flow of ingress or egress. If it matches, then kill it. Where to put it depends on your configuration. But more often, most of our configuration is still at the entrance. Including the recommendations on various textbooks, are also configured at the entrance. When you learn IE in the future, you will find that it is useless to hang some strategies on the exit. Less involved in Cisco. So we often do more configuration at the entrance. For equipment, if you want to make the ACL take effect in the future, you must mount it under the interface. Hooking can also be called calling. The idea of configuring the entire ACL is actually very simple. Assume 3 steps. First, define the parameters for ACL matching. Second, after matching the parameters, you also have to define its matching action. Third, you hook this ACL to a certain direction on a certain interface. Because the interface has an inbound and outbound direction. Therefore, the outbound direction and the inbound direction have to be mounted again. Otherwise, you can't make it reachable. Before we do ACL, make sure the network is reachable. If the network is unreachable, then you do ACL is meaningless. That is, the network must be able to communicate first. Let's look directly at the environment. The experimental configuration of this environment topology will be discussed in the next class. The current requirement is to prevent PC1 from pinging PC2. Before realizing this requirement, first, ensure that PC1 can ping PC2. Then configure on this basis. If the network itself is unreachable, then you do ACL is meaningless. It must be based on the original normal communication of the network. Then based on some refinement, do some corresponding configuration for it. So you must ensure that the network is reachable. For this picture, let's talk about the configuration idea first. But don't configure. Make PC1 unable to ping PC2. That is, cannot ping this device from this device. If we go to ping, first of all, the 2 devices need to configure the address and gateway. For example, they both run OSPF through. Then how can we put some restrictions on it? Suppose now we have 2 ways. If I use the basic ACL to match the source IP of PC1, then we give it to deny. I make a configuration on the ingress interface of this device. As long as it is traffic from PC1, I give it deny. Then PC1 cannot ping PC2. But this does not optimize. ACL has a principle. ACL is as far as possible in the case of meeting the demand. Minimize the impact on other network. Now PC1 just doesn't want to access PC2. If under this interface, kill all traffic from PC1. Then PC1 can't access R2 either. PC1 can't access R1 anymore. If R2 is connected to other PCs, PC1 can't access the following PCs either, because all its traffic is killed here. In fact, this does not meet our real needs. Our requirement is just to make it unable to ping PC2. It's not that it can't ping all other devices. So it is not very appropriate to use basic ACL here. For us, we can't use basic SL. The final effect achieved is that PC2 cannot be pinged. But other devices can't ping. It's not what we want. So we're going to use an advanced ACL here. Actually, we are at work. Including you will do a lot of configuration in the future. You will find the basic ACL uses less than the advanced ACL. Our more or finer matching. Because to determine the smallest range of influence. I'll give you a simple example. Let's take a look at the PPT. For example, now I hope to let this 1.0 network segment access the internet. But don't let it access the server. There are two options. The first one only grabs the traffic that wants to go to the server now. Then just kill the traffic. Suppose this server is on the 3.0 network segment. What I need to grab is some data in the network segment from 1.0 to 3.0. Then kill it under this interface. Then it will only affect the network segment 1.0 to 3.0. It can't access the server. But now if I now want it to not reach the server, I match the 1.0 network segment. The entire network segment is gone. Then kill it under this interface. Now this 1.0 network segment can't connect to the internet. Not only can it not access the server, I can't get online now. So this is not a real requirement. The same is true for this graph. Just don't want to ping it now. And don't want to have more control over some other range. So we now use the second method. Advanced ACL. It can match based on more parameters. For example, source IP, destination IP, and agreement. We don't actually use the port today. The whole NA stage does not involve too many ports. When we talk about NAT in the next class, I will talk about the port problem. In this lesson, we only need to look at these three parameters. The configuration including the next lesson is also based on the three of them. Now PC1 can't ping PC2. These are two hosts. I can limit traffic from 10.1 to 20.1. Guaranteed other data traffic. As long as the source and destination cannot be strictly matched. Then traffic will not be affected. Followed by the matching protocol. Ping uses the ICMP protocol. Right? There are two kinds of messages in ping. One is called echo. One is called echo reply. That is, one is request. One is reply. Actually, if the ping fails, it can be configured for both packets. For example, I'm here to kill its echo. That is, the request message. It is also okay to kill its reply message. Because ping is bidirectional. Data used to have to be returned. This message has two. If a message does not come back, it will not come back. But still that sentence. I prefer to kill the data when it passes. So we usually do some actions for ping. For example, ban ping. We are more based on echo to configure. Let me talk about its configuration ideas. We go up ACL on this device. Let it match the data from 10.1 to 20.1. And the protocol matches a subfunction like echo in ICMP. All future data from 10.1 to 20.1 want to use functions like echo in its ICMP. All will be denied by this interface. It cannot send this request. It means that PC2 cannot receive its message. Won't reply to it. Then it can't ping. Here are some rules corresponding between them. Let's talk about configuration in the next class. There will be a wildcard mask in the basic ACL. OSPF and EIGRP we talked about before. In fact, the anti-mask is used. At that time, I seem to mention wildcards with everyone. When we are doing basic ACL configuration, wildcards will be used. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.